Hello everyone. In this video we're going to go over section 9.3 class note problems. So we're going to go over working with sets and the exclusion and inclusion rule. So first let's go to question number 1. We have 80 students in the dorm hall and 38 of them are taking at least one English course, 24 are taking at least one science course, and 8 are taking both science and English. So the question is, what is the probability that a randomly shows a student is taking English or science? So we're gonna call E the set for English and S the set for science, and E inter S will be English and science. E union S will be English or science. So we want to pretty much find out what is the probability of doing English or science, but by the rule of the inclusion exclusion, we know that this is going to be the probability of English plus the probability of science minus the probability of both. Okay, so it's going to be very useful for us to find how much is each of this. Now, that information is going to come from here. We have 80 students on a dorm, and 38 are taking at least one English course. Because those 38 might include people that are taking science, we cannot take that into account yet. It says 24 are taking at least one science course, same scenario. And so what we're going to start is with this 8. That says 8 are taking both English and science. So this 8, they go in the intersection. And so we get the cardinality here of the intersection, the number of the intersection. And now, once that we have this, then we can find out what are the others. We have 38 are taking at least one English course. But we already have 8 that are taking English. So here we're going to have 30 people that is taking only English. And so 38 is total of the people that are taking at least one English course. They might be taking something else. Now, same applies with science. 24 are taking at least one science course. But that means that since we have 8 that they're taking science, but they're taking English, so there needs to be 16 here. 16 plus 8 is 24. Now, is that the total? If you think about it, we have 30 plus 16, which is 46. And with this is 54. So in total, there's going to be 26 students that are taking neither of those. And it's out of 80. Now, we pretty much got all the important information here. We have the 38 and we have the 24 here. So we can calculate the probability. The probability of E union S is going to be the probability of E, which is going to be the number of elements in E over the total. The total of elements in E is 38 out of 80 plus 24 out of 80 for those that are taking science. The probability of taking one of the students on science is going to be 24 out of 80, but we remove the intersection, which is the people that is taking both, so it's going to be 8 out of 80. Now, we can simplify this out, and this is going to be 30, 50, 58, 62. So 62 minus 8 is going to be 54. So this is going to be 54 over 80. Or we can simplify this more, and it's going to be 27 over 40. Okay? And that'll be the probability of getting someone there. Now, question number 2. We changed gears now. We're going to be working with probability of not rolling a 4 when we're doing a fair dice. So the thing is, not rolling is a complement. So probability of not 4 can be seen as 1 minus the probability of 4, of rolling a 4. And now in a single die, the probability of rolling a 4 is 1 out of 6. So this will be 5 out of 6. And that's it. Question number 3 talks about a certain company password must be between 3 to 5 symbols using 26 letters and 10 digits and 14 special symbols. So we have 50 symbols in total. So we want to know how many passwords are possible if repetition is allowed. And notice that because we have options, we can have a pen of 3 numbers, but we can have one of 4, and we can have one of 5. So those are 3 completely disjoint sets. And so the situation is going to happen that I need to count each of those situations and add them up because they're going to be independent. So notice that if we're picking password with repetition allow, then this is going to be 50 power to the 3, this is going to be 50 power to the 4, and this is going to be 50 power to the 5. And the total is going to be just the sum of those 3 situations, since they're independent. Okay, those are all the possible things that are going to be allowed, and this is a gigantic number. If you put this in your calculator, this is going to be like 318,875,000. Now, how many passwords contain no repeated symbols? So for no repeated symbols, we're back again to establishing this. And so now we have 50 times 49 times 48. And here I have 50 times 49 times 48 times 47. And here 50, 49, 48, 47, 46. Okay? So you can also think of this as how many permutations you're getting out of 50 with 3, plus how many permutations you're getting from 50 out of 4, plus permuting 5 in 50 symbols. So that's the 2 ways that you can go about this, by the multiplication principle, each of these pieces. But notice that this is equivalent to the permutation. So here's a permutation with 3 elements, permutation with 4 elements, permutation with 5 elements. If you made the calculation with the factorial, you're going to notice that this is equivalent to this when you're multiplying, when you're simplifying the factorials. At the very end, then this is going to give me a very large number. This is going to be 259,896,000. Now, we want to know how many passwords has at least one repeated symbol. And one repeated symbol, probability of at least one, it can be easily seen by complement as 1 minus the probability of no repeated symbol. Remember, if I have no repeated symbol, the opposite of no repeated symbol is at least one repeated, right? So that's why we can use this probability. This is very difficult to find by itself, but if we use the complement, we can support ourselves on the previous answer. Okay? Or, sorry, this is the probability. So I should be thinking more in terms of not the probability, but the set cardinality. So instead of using the probability, we're going to get the number of at least one is equal to the total minus the number of no repeated symbols. So the probability of at least one is going to be this total here that we have, the 318,875,000, minus the no repeated symbol, which is going to be this 259,896,000. And so subtracting that, this is going to be 58,979,000. And so now we can actually think about the probability of that. How much is the probability of at least one? That will be the 58 millions out of the 318, which is pretty much what I was getting here, but I got a little bit ahead of myself. You can always count the set first and then do the probability, but you can also do the probabilities by counting each of the pieces. All right, so now let's go to question number 4. How many integers from 1 to 1,000 are multiples of 3 or multiples of 5? So notice that the total of elements from 1 to 1,000 is something that we can find with 1,000 minus 1 plus 1, so 1,000 numbers. So we're not going to really delve too much into that since it's not interesting, but we can think about how many possible multiples of 3. So let's call M3 multiples of 3, and it's going to be 1,000 divided by 3, and we can get like kind of like the floor of that, and so that's going to give me 333. And multiples of 5 is going to be once again the floor of 1,000 divided by 5, which is going to be 200. So nothing especially there. So it says how many integers are multiples of 3 or multiples of 15. So if it's going to be multiple of both at the same time, that will be the multiples of 15. So that will be take 1,000 divided by 15. And so that's going to give me a total of 66. So now by inclusion exclusion, what I can say is multiples of 3 or multiples of 5, then the amount of that is going to be equals to the multiples of 3 plus the multiples of 5 minus the multiples of both, which is the multiples of 15. Okay? And so that'll be 333 plus 200 minus 66. And so that's going to be around 467. Now to answer how many neither will be the opposite. Neither will be 1,000, which is the number between 1 and 1,000, minus 467, and that'll be 533. So that way we can get to count that. Question number 5. 4-digit pins form from digits 0 to 9. What is the probability that a pin has at least 2 identical digits? So notice this, at least 2 identical digits, and we want to do the complement. So the way that we do this is at least 2 identical is 1 minus the probability of none identical, all distinct digits. And we know how many distinct we have in total, because if it's a 4-digit pin and it's going from 0 to 9, then each of the entry has 10. So this is like 10 to the 4. So 10 to the 4 is the total, right? So the total is 10 to the 4. And now this distinct digits is going to be 10 times 9 times 8 times 7. Because the first one has 10 digits to choose, the second one has 9, the third one has 8, and the last one has 8. Okay? And so this is 5,040. So the probability of this will be 1 minus 5,040 divided by 10 to the 4. If you find what that number is, this is approximately going to be 0.496. Okay. All right. So now finally for question number 6, we have a survey of 200 students, and they own either a laptop, a tablet, or a smartphone. And we have information about who owns what. And we want to know how many students own at least one laptop or tablet, and what is the probability that randomly choosing a student owns a laptop or a tablet. The way that we do this is, once again, we start by the common things, and we start filling out from the inside to the outside to allocate all these 200 students. So we're going to start with 5 that owns the same 3 devices. So we have 5 here. Now we have 13 that owns a tablet and a smartphone. So tablet and a smartphone are 13, but we already have 5 here. So we're going to go with 8 here. Now we have that 15 both a laptop and a smartphone. We have 5, so we're going to get 10 here. Now 20 on both a laptop and tablet, so we need 15 here. Okay. Now we have 48 on a smartphone. We have 15 here. 8 here. So to get to 48, I need 25 more. So 25 and 15, 40, 48. 63 owns a tablet. So we have 20, 28, 28 and 63. So I need 35 more. And finally, 80 on a laptop. But here we have 30, so we're going to have 50. And so now the total, to get to 200, we add everything up. So this is 80 here, plus 25 more is 105, 148. So the total outside is going to be 52 of people that is not inside of any of this. So now, how many students own at least one laptop or tablet? So the number of students that has laptop or tablet is going to be the number of students with laptop plus the number of students with tablet minus the number of students with both laptop and tablet. And so we can find those numbers. Total with laptop is going to be 80. Total with tablet is going to be 63. And minus both laptop and tablet is going to be 20. So this is going to be 123. Yeah, the probability of laptop or tablet will be 123 out of 200. But this is just this question. Now, if we're going to get at least one device, we can see the probability at least 1 is 1 minus the probability of none. But this is just 1 minus the 52 out of 200. Since pretty much we have 52 outside that they don't have anything. So this is going to be 148 out of 200. Okay.